Alrighty then. So this little video will be fairly short. It's going to be about the idea of correlation. You've heard it used, maybe you've even used it yourself. You said, there's no correlation between what you said and what's going on. The idea is it's a relationship. Okay? And it's actually a mathematical term. It's a mathematical relationship. And what we want to know is this. You have x's and you have y's. And you're going to make a scatter plot. And unlike a time series graph, it's not a connected scatter plot. It's just, look at that thing. It appears as x increases, so does y. And so because that's true, so does y, we say that's a positive correlation. And if it looked like this, it'd take a rocket surgeon to think that would be, negative correlation. In essence, you could draw a line, something like that through them, it'd be linear, and it would have a positive or a negative correlation. And of course, well, between negative and positive, of course, you've got zero correlation. Zero correlation looks something like this. The idea that it's all over the map. One of my favorite examples is this. I feel like by the way, this is why I'm not an artist. I am not trying to flip you off. That looks goofy. There, well, no. There we go. Whatever. So people with longer is it ring fingers? Pointer fingers. People whose pointer fingers are longer have a higher IQ. So you could have pointy finger length. And you could have IQ over here. And what you would see is, yeah, it's pretty much the same. Similar deal. Here's people's eyes. If you measure the distance between their eyes and then their weight or some such, like, there doesn't seem to be any correlation here because there are big fat people who have little itty bitty beady eyes, and there are other people who are really skinny who have wall eyes, and everywhere in between, because these have no relationship to one another. It is the classic question. What does that have to do with the price of tea in China? Nothing. There is no relationship. Okay, so these are the classics: zero, positive correlation, negative correlation. Now, by definition, R is correlation. That's the word, that's the variable we use for it. It is always somewhere between -1 and +1. +1 means it is perfectly linear. That is, all the points lie on exactly a straight line. Boom, 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 boom. That is a straight line. Every point lies on it. That is 1-to-1. That's one correlation. -1 is also perfectly linear. It looks like this, or similar. In either case, in the real world, and I have to be careful because my friend teaches chemistry, he always makes a big deal about this. He tells kids, hey, look, your R needs to be 1 exactly in chemistry. Well, yes, in chemistry, when you add this much of this stuff, this reaction will happen every single time. Take it to the bank. That's why it's science. However, in the real world, anytime you have to deal with people's responses, the way things, the way things interact with this and that, there's always going to be some, slop. And it could be fairly linear, like this guy here, you see. But it's not 1-to-1 because it's not a 1 correlation because it's not perfectly linear. Okay, there's always going to be, error. That idea that people are weird. That idea that not everything works the same. And by the way, it's true, not just people. You could be working in a manufacturing process. You're going to have, this is our target width of the hole we're trying to drill, and you got machines and robots doing it all. And it's still not going to be perfect every time. There's always going to be a little bit of slop. That's just how life goes. But almost in general, when you're doing statistics, if you get a 1 or a -1 correlation, you can be sure someone's been screwing with your data. Okay? Unless your sample is, I'm trying to figure out how much tacos cost over at Taco Bell. And I feel like I got 2 tacos for this much and 3 tacos for that much. And you're like, well, okay, that is a linear function. But any other situation out there in the real world, it's going to be a little off. One of my favorite ones of all time is I've always asked students, what is your age? I did I should be careful. I do this in the high school classroom and their mom's age, which is always funny when I know one of their moms and they're like, oh my God, my mom's going to be so mad you asked that question. I'm like, relax, we're like the same age. So whatever. Anyways, and what you'll see is this. You get a 17-year-old, you get a 36-year-old mom. Okay, whatever. And then you got an 18-year-old and you got a 42-year-old mom. And then you got an 18 and a 39 and an 18 and a 47 and then a 17 and another 40 and then you got a 17 and a 53 and then you've got a 19 and the kid's really old and that's really strange and a little weird, and a 32 and that's weird. Yes, it is. And then 17 and 63. Okay, my best friend in high school, it was kind of like that. My mom was like 40, I don't know, 2 or 3 or something, or 4 or 5 when I graduated from high school. I don't know. I have to think about that for a minute. 43 probably, I guess, when I graduated from high school. And his mom was probably 63. He was in a whoops. But that's how it goes, huh? But interestingly to note is that, hey, look at that. When you graph this, what? Oh, look, here's a kid. Here's the mom's age, right? And then here's the 17-year-old. Since they're all pretty even, we could do it like this. Here's 17, 18, 19-year-olds. 17, we got a 36, and you got a 40, and you got a 63. That's weird. And then you got an 18, you got 39, and a 42, and a 47. And I feel like I'm missing a few 40s. 17, I got 36, and a 40, and a 53. Oops, I missed a 53. Anyway, what happens occasionally with this situation is you'll see that, weird. You could kind of draw a line through it. It's kind of a terrible line. It's not a very good correlation at all. But in this case, the correlation is actually, it's negative. Now, what does that mean? It means as the kids get older, the parents get younger. I had this one class one time where that literally happened. All the old kids had young moms, and all the young kids had old moms, and it literally was going downhill. If you wanted an equation for that, it was something like y equals like 30, like 30 minus x or something. It was ridiculous like that. One time I did it, and I kid you not, instead of having a 1 slope, that is the kid got a year older, the mom got a year older. No. It was like a 2.5 slope. It was the weirdest thing I've ever seen in my life. But that's how life goes sometimes. You're going to have situations where, you got pregnant when you were 13 and you had a kid and whatever. And so your kid at 18, you're pretty young by comparison to all the other moms. Okay? Or it could be like my friend Nathan's mom, who was really old in comparison to all the other moms. Yeah, that's how these things go sometimes. Because life isn't perfect that way. And that's what's kind of cool. I always thought about correlation. When I look at it, it doesn't mean, first of all, it doesn't have to be a 1 correlation. It'd be nice if it was, but, it's if I want to prove if medicine works, yes, I would like it to be that the more of this drug that I give you, the cancer shrinks. I'd like it to be a negative correlation, right? I'd like the tumor to shrink, perhaps. I would like there to be some correlation to the amount of time I spend working with a student on their grades to what actually happens with their grades, right? With their math grade. I'd like that to happen. So I'd like it to be a positive correlation, like their grade to go up over time. That's kind of what I'd like to see, okay? And so there's this idea of correlation. People always tend to think that correlation means causation. It'd be nice if I could write causation, but it doesn't, okay? Just because there's two things that are correlated or they're related doesn't mean that one causes the other. Sometimes it's what we call a causal relationship. That is, they both are responding to something else. Okay? And so they look like they're related because they're both related to something else. Okay? So just kind of how it is. So one of my favorite ones of those is bikinis and ice cream. Okay? This is a fact. I didn't make this up. This is a well-known fact. The bikinis and ice cream are highly correlated. Now, when I say highly correlated, I mean there's a strong relationship there. That does not mean that if you start putting on more bikinis, or you start seeing more bikinis out, all of a sudden ice cream is going to go up. That's not causing ice cream to go up. They both are related to the temperature. So in the summertime, you're going to likely see more bikinis. Okay? And in the summertime, you're probably going to sell more ice cream. That's just kind of how life goes. They both are dependent on temperature. Okay? If you look at that, as the x-axis down here, which is bikinis, gets bigger, as it heads towards 60, the amount of ice cream also goes up. Okay? Now what you can do is right-click on one of the points. Oops. Give it to me. Why aren't you giving it to me? There it is. And notice down here it says add a trend line. Okay? When this happens, the trend line pops up. That's that line I was kind of tending to draw through there. And Excel always starts off with a linear fit. That's all we're going to talk about. But you can click on it right here. And you can do two things. First of all, we can display the equation and we can display r squared on the chart. Okay? Now, what is r squared? Okay, well, we need a definition for that as well. First of all, clearly it's just, well, r squared. R squared is what is called the coefficient of determination. Okay? It is the percentage of the change in y that we can attribute to a change in x. Okay, that's great. That's by definition. Now, in the case of two variables where one's not doing the causing, where this is just a casual relationship, doesn't really mean much. So in the case of r squared equals 0.89, r is equal to the square root of 0.89, which is 0.9 something, which we can actually ask Betsy over here. Oh, great and glorious Betsy. Oops, that's a little ridiculous. Find an empty spot. Get my screen up here. So I'll just go equals, and then SQ. Why aren't you typing? Equals. Try that again. Equals SQRT. That's square root, by the way, of 0.89. So 0.94. So because that is so close to 1, we say it's highly correlated. What does that do for me? It allows me then to predict the amount of ice cream based on the number of bikinis I see. So if you look on the screen, what you saw up here was you saw an equation. It was 0.85, well, I'm going to say 0.86 minus 2.96. And the idea is, if you tell me you saw 100 bikinis, I would say to you, okay, well, whatever. Actually, I wouldn't say. Would I say 100? Let's look at our data. Our data is nowhere near 100, is it? So because our data is nowhere near 100, I'm not going to do that. I'm going to say around 60. If you said you saw 60 bikinis, I would tell you that I would expect to sell this much ice cream. So I would take my calculator and I'd say, all right, equals, actually I'm going to get a different calculator. That's kind of annoying me. No, good try. Now maybe if you get the other 0 in there, that would help. There you go. You would expect to see about 48.6 ice cream cones sold. And that'd be a pretty good prediction because R is so large. That is a good fit. So this prediction is good prediction. Notice, Suppose I said to you, well, how much ice cream would you sell if you saw 200 bikinis? Well, the first thing you should ask yourself is, where did this equation come from? This equation came from this data. The most bikinis you ever saw was 56. That's it. That's it. How close to 200 is that? Well, it's not close at all. It's about as far away as you can get. And in the real world, a person might think to themselves, wait a minute, if all my data was down around, 50 or less, why did 200 show up? In a situation like this, what a person might say to themselves is, you know what, I bet there's some special thing going on in town. I wonder if, because there's so many more people in town, I wonder if there's going to be some sort of different relationship, in other words. And the idea is, what we call this extrapolation. Because we are trying to predict for an X value that is nowhere near where our original data was. Our original data was anywhere from like 0 to 55, 60 or somewhere in that neighborhood. And we're asking to go out so far out to 200. To any prediction I make out here is, well, it's kind of a crapshoot. I mean, it's like, what's the weather going to be tomorrow? I feel pretty good about the weather forecast. What's the weather going to be the day after that? I feel pretty good about that. What's the weather going to be like 2 weeks from now? Well, it's Oregon, so probably rain. But I can't be as sure 2 weeks out as I can be, tomorrow, because it's a lot closer. It's near where we built the model around. So I can predict for this. I can whip my calculator out, and I can say, oh, Betsy, what is 0.86 times 200 minus 2.96? And lo and behold, I expect to see 169 bikinis. Ice cream. I can actually predict it, but I'm not going to go on a limb and say, hey, that's going to be a good thing, because extrapolation is a bad thing. That's where you make mistakes. That's where you say, hey, look, we've built this model over the last 100 years, and we're going to predict out now 100 years into the future. Well, you can predict it, but too many things happen between now and then. Nothing's going to stay the same. There's no such thing in that regard as homeostasis. Things do not stay the same over that length of time, especially when it comes to like budgeting or our environment. Things change too much in order to say, hey, everything is staying the same. This is the exact pattern we expect to go on forever. It will not work that way. I made a couple other ones over here. Hours spent studying and your grade. I would expect this to be a positive correlation. That is, like, the more I study, I expect my grade to go up. First of all. Second of all, I think this person here, I'm like, 7 hours, she only got an 83, or he only got an 83? Probably. And you know why? Because that's that person who works their tail off in a particular class, let's say a math class, and still struggles with it. That happens. Okay? And look at this person. This sucker here barely studied at all, got a 90. That was me, by the way. Sorry. In math classes. In other classes, not so much. I didn't have to work at it as hard as some people did. That's fine. But in other classes, I had to work a lot harder. So we all have our little, ups and downs. But there's always going to be a slop like that. It's never going to be perfect. If it was, well, that would just be weird. Hey, look, it does look like it's a positive correlation. Now, I would like to point out, if I can get this freaking thing to agree with me, there it goes. I would like to point out that on this graph, I didn't need to go all the way down to 0. Okay, and I needed to go most of the way to 100, but I didn't need to go all the way to 0. So I'm going to pull up my keyboard here real quick. What are you doing? Why is that not working? There it is. Whatever. And if you double click on this thing pops up, and you can say, well, let's just go from 50. There we go. That's a little nicer. And so you can see the trend is up, but of course there's weirdos that throw things off here and on the top end. Again, if you right click on one of the points, add a trend line, hit display equation, hit R squared. What you'll see is the R squared is not very good. It's 55%. Okay? So if I take the square root of 55, 0.55 rather, square root, I'll see it's 0.74. Now, R of 0.74 isn't bad. It's not great, but it's not bad. It's positive, so I'm not shocked by that. But it's not a great correlation. I can still predict from it, but I may or may not get the best results. Notice what this is saying to me right here. I get 5x plus 58. In other words, we're going to start at a 58 if you don't study at all. You spend 0 hours studying, you will start off with a 58, 59%. And you're going to add 5%, what this is saying. You're going to add 5% per hour you spent studying. That's what that formula is saying to me right there. Okay? Here's another one. Age versus blood pressure. You're thinking to yourself, I didn't think age really affected it that much. I thought it was more like if you're fat or out of shape or you had some predisposition to it. I don't know. Let's see what happens. By the way, I made this data up like I make up all of my data. You're like, geez, it's just a cloud. It's a mess. And you're not wrong. I look at that data and I think to myself, ugh, I bet if I drew a line through it, it would be horizontal. And it is. Huh? Look at that. Friends, you can't get any closer to 0 than an r squared of 0.004. If you square rooted that to find r, you would find that r is 0.06. That is as close to 0 as you can get. In other words, what we're saying is this. There is basically no change per year. In other words, for every year you get older, your blood pressure goes down by 0.055, which is diddly squat. It's basically 0. In other words, it's basically not changing at all. In other words, another way of saying that is, look, the average blood pressure of this group of people is 127. That's for the top one, whatever that's systolic, I think. So that is an idea, the example of a 0 correlation. In the real world, you'll never get exactly 0. It'll be awfully close to 0. Okay, but not completely 0. And then this one, the number of coats, the number of bikinis that I see out on the street. Geez, I feel like, oh, by the way, let's back up a train. So casual, this is homework versus studying. This one to me sounds like causal. Age versus blood pressure, well, there's no correlation at all there. This one, it seems like there is going to be correlation, but it seems like it's probably negative because the more coats I see, the less bikinis I'm expecting to see. And the relationship is casual because one's not causing the other one, but they both are related to, again, temperature, perhaps. Okay? And so it looks like for every one more coat I see, I'm seeing a half of a less of a bikini. Right? So, remember, here's the dealio. Oops, come back. So, where X is the coats. So, for every extra coat, I see a half of a bikini less. And, again, I must be, if there were 0 coats, I'd have 63 bikinis, is what that's saying to me. Square root of 0.96, that would be my R. Square root of 0.96 is 0.98. Okay, that's our correlation. That is a phenomenally good correlation. That's so high. So if someone asked you to say, hey, look, if there were 80 coats on the beach, or 80 coats out, I guess they wouldn't be on the beach. Well, in Oregon, they might be on the beach. Who knows? How many bikinis would you expect to see? Plus 63. Okay. Then you'd break out your calculator and go, all right, well, I can punch this in. Negative 0.52 times 80 plus 63. For whatever reason, the 0 is not working. Give it to me. I'd expect to see about 21 bikinis. Okay? Well, if you come over and look at it, 80 is one of the numbers, is in the range, in the realm of numbers that I was predicting for, so that actually makes a lot of sense. Notice if you come over to 80, it'll be right about there. It'll be about 21 bikinis around the line. It looks good right there. Okay? Again, I couldn't predict for negative coats. It doesn't even make sense. I could probably predict for 5 because that's pretty close to 11 on the bottom end. On the top end, if you wanted to predict for 200 coats, I would laugh at you because that'd be weird. First of all, at 120 coats, there were no bikinis on the beach. Don't think I'm going to see negative bikinis. But second of all, my data only went up to about 120, 121 there. So if I tried to go out way beyond that, say 200 or 250, even 150 would be a little suspect just because it's so far out from where we are, all right, from where we got our data from, okay? So our data is pretty good in this realm, or anywhere fairly close to it. If you go out a long ways from there, not so much. That is the idea of correlation. I think you'll find it to be a fairly straightforward deal. Most of the things in this book are not so much about the math of it. It's more of the relationship aspect of it. I personally can't really teach one without the other. So the idea here is correlation is a relationship between two variables. Okay, it can be causal or it can be casual, and then a person has to decide whether they think it's causal or casual. Clearly, some people assign causation where it doesn't exist. I will mention this story several times, I'm sure. I usually go to it. It's one of my go-to stories. My friend, he's always, whenever he gets sick, he goes to the doctor. He always gets some medicine. And it's just happened on numerous occasions where I've called him up, hey, how you doing? He's like, oh, I'm been sick all week and stayed home. And, oh, yeah. I got some medicine. I sure feel a lot better now. I'm like, oh, did you go to... Oh, no, I guess that's when I say, did you go to work this week? No, I've been sleeping all week. So you didn't even work from home? No, I've just been sleeping. I'm like... So he always attributes that healing of his cold or whatever to taking the medicine. But he doesn't take any consideration in the fact that maybe it was sleeping all week that really helped him out, right? So sometimes we have this idea that we can assume a false causation. We'll talk more about that when we get into logic later on. But the thing to remember is if we give a certain dosage to these people and a certain dosage to these people or plants, it could be plants and fertilizer again, whatever it is, and we could see then, well, if you give this much fertilizer, these plants, each one of them put out a different amount of plants or tomatoes, for instance, and then if you put on more fertilizer, they put on a different amount, and then you can see that for every pound of fertilizer we add, we're going to get this many more pounds of tomatoes. Okay, hopefully that's a positive correlation. I mean, it'd be weird if you put more fertilizer on and got less tomatoes out. Okay, so that's mostly what your book talks about is the big picture overriding concept of it. But that's how it works, and so just keep the big things in mind. It's a relationship. It can be causal or it could be casual, and there you go.